Assalamu alaikum, lovely students. We're back with another video lesson. Last lesson, or in the previous lesson, we did talk about wavelength, we talked about period, we talked about frequency, and we talked about wave speed as well. So now let's go through each one of these real quick. We said wavelength is basically the distance between two consecutive troughs or two consecutive crests, or more formal or general definition would be the distance between one point on a wave to the same exact point on the next wave. That is one wavelength, and we said it is measured in meter. And then after that we talked about frequency, which is basically the number of vibrations or cycles per unit time. And then after that we talked about period as well. We said period is basically the time it takes for one complete oscillation or for one complete cycle. Frequency was measured in hertz, and then period is measured in second. And then after that we talked about wave speed. Yeah, basically wave speed is how fast the wave is traveling per unit time. And of course we had an equation for that. Let's say that is normally how it is. And then we said wave speed can also be, or the equation for wave speed equal to frequency times the wavelength. Yeah, very good. Wave speed was measured in meter per second. And then we stopped at this point right here. So we have this question, which is very important. Says a wave traveling in a positive x direction with a frequency of 25 hertz, yeah, it is then, or you can say, which is of course is shown in the figure below, find the following values of or for this wave. Okay, now let's find these or try to find what they are asking us to find. Okay, first of all, let's get this prepare this for calculations. Let's get the mouse, move this one up. Okay, I think right, where did this go? Okay, now, perfect. So the first thing that we want, or they need us to find, is the amplitude. Do you remember what was the amplitude? We said amplitude is basically the maximum displacement, either above the equilibrium position or below the equilibrium position. But do we have, like, or can we find the amplitude directly here? No, but something else is given, yeah? Remember, the whole distance is given, so this distance is basically this, yeah? And of course that means this is one amplitude up, and of course one amplitude down. If this is 18 here, what is half of 18? That means there is 9, but remember this is in centimeters, so 9 centimeter up, 9 centimeter down, so we can say amplitude here, or this distance here is 9 centimeter, or just simply amplitude is 9 centimeter. Can we convert it to meter? Yes, of course, that is going to be 0.09 meter. All right, what about the wavelength here? Now this one also is very important. Remember, in order to find the amplitude, the wavelength first. What is the wavelength here? We do know that, or previously we said the wavelength is basically, let's say, let me move this down a little bit. Okay, now the wavelength previously we said it is the distance between, let's say, two consecutive crests, or two consecutive, let's say, troughs here, correct? Or the distance between one wave to the same exact point on the next wave, let's say. But what you see here, and we said if you're not sure, if you're not certain, we can use the amplitude to find the wavelength here. We said for one wavelength there must be what? There must be four amplitudes here. So this is basically the distance from this point all the way to this, that is basically one wavelength here. But I don't have one wavelength here. What I have is basically the distance between this point all the way to this. Now, there are two ways where I can find the wavelength here. We know that, first of all, the distance between a crest, let's say, crest to a trough, is basically half a wavelength, 1/2 wavelength. That is one way to know, okay? That is one. Second of all, if we use the amplitude theory here, okay, so remember we said there are 4 amplitudes in every wave, yeah? But the distance between this to this, that means it can only give me 2 amplitudes. And you do know that 2 amplitudes, that is going to be half of a wavelength, yeah? Half of what? Half of a wavelength. So of course we can say, by the way, half of a wavelength equals to what? Equals to 10 centimeter, okay? 10 centimeters. So what would be the wavelength here? Of course, you can cross multiply or multiply both sides by 2. Then wavelength will be 20 centimeter. So this is one wavelength. Okay. Next, this says find the period. How do we find the period? Can we find the period here? Well, not enough information on the diagram, but what you need to know here is we're given the frequency. So if you're given the frequency, can you find the period? Yes, and that is very simple. And how do we do that? We'll say frequency equal to 1 over the period, yes? Okay. Or basically period here, should have wrote this one first, period equal to 1 over the frequency, yeah? So we want the period here, so 1 over the frequency, which is 1 over 25, and of course 1 over 25, not 12. 1 over what? 1 over 25, and of course this would give us the period in seconds. So what is the period? Let's find the period there. Okay. I think I'll have to do this. Okay, so the period is going to be 0.04 seconds. Okay, now the next one says find the speed. And how do you find the speed, by the way? Okay, now you have all the information you need to calculate or to find the speed, yes? Okay, now speed or speed of a wave equal to wavelength times the frequency, yeah? So speed of a wave, okay, equal to, let's say, frequency times wavelength. Now we do have the frequency, which is 25, yeah? Now we did find the wave as well, yeah? The wavelength, but remember this is 20 centimeter. We don't use centimeter, we'll use meter, yeah? So in this case, it's going to be 0.2 meter. Okay, 0.2 meter. Okay, so now 25 hertz multiplied by 0.20, and that is, of course, equal to, let's say, 25 times 2, that is 50. So there's one decimal, is going to be 5 meter per second, and that is the speed of the wave. Okay, this is how it is done. The key idea, it is right here. Half a wave, this distance that is given, let's say it's half a wavelength. So one wavelength will be 2 times that, okay, which is 20 centimeter. Convert the centimeter into meter, and then you're given the frequency, you can find the speed of the wave. All right, now we have question 26. It goes like, microwaves travel at a speed of light, which is 3 times 10 to the power 8 meter per second. When the frequency of the microwave is 9 times 10 to the power 9 hertz, what is their wavelength? Okay, now that is simple question. This is just the application of the equation, and that's it, yeah? It says find what? Find the wavelength. So wavelength equal to speed. Remember, since it is speed of light, I can use c. If not, you could just go with v, that is also fine, divided by the frequency. So speed, that is 3 times 10 to the power 8 meter per second, divided by the frequency, which is 9 times 10 to the power 9 hertz. And then you calculate that one, you will get 0.0333 meter, or you could just say 3 times 10 to the power negative 2 meter. Okay, this is, that was easy enough. Okay, now take a look at this one. This is also an interesting one. What does it say? It says, okay, it says, Lawrence dips his finger into a pan of water twice each second, yeah? Producing, okay, so basically, we could say something like this. If this is a pond of water, whatever, so there's Loan, of course, let's say, is dipping his finger into this, let's say, twice every second. So if I change this one to, let's say, frequency, remember, twice, that means 2 times every second, so in 1 second. So we can say the number of waves here, or the number of vibrations that happen to the surface of the pond would be 2, yeah, in every second. So number of waves, or you can say vibrations, that is 2 every second. So of course the frequency will be 2 hertz. Now I found the frequency without reading the entire question, so let's see what it is. Okay, into the pan of water twice every second, producing a wave with crusts that are spread by 0.15 meters. So of course we have waves now. Let's say, or if I draw this one here, or complete this one here, these crusts basically are, I can turn this one into a crust. Let's use blue here. So we can say if this is resembling crust, and then another crust here. So these these waves has to be symmetric, by the way. So this distance between one crust to another is basically 0.15 meter. I can draw the crust here again. right? So basically, this is a little bit higher, but that's all right. So the wavelength becomes 0.15 meter because it says the crests are separated by 0.15 meter. Okay, so what is the question? Determine the frequency, period, and speed of these water waves. So first of all, we said we found the frequency without even seeing the question because he dips his finger twice, so 2 vibrations in 1 second. So number of waves divided by second, so 2 divided by 1, that is 2 hertz. So the frequency, right? The frequency for this, for these water waves is going to be 2 hertz. Okay, that is the first one. Now, what about the second one? Second one says find the period. Of course, if we know the frequency, we can find the period. Period equal to 1 over the frequency, so 1 over 2, and of course that is 0.5 seconds, yeah? Very good. And then the third one says the speed of these waves, yeah? Now remember, to find the speed, we need frequency and wavelength, correct? And we have them both, yeah? The frequency is basically, what is the frequency? 2. The wavelength is, what about the wavelength? It is 0.15 meters. So that is basically 2 times 15, that is 30. So 2 decimals is going to be 0.30. That is going to be meter per second, since it is wave speed. Okay. Now, moving on, it says the notes, we have question 36. The notes produced by a vibrating citron range in frequencies from approximately 196 hertz to 2637 hertz. Find the possible range of wavelength in the air produced by the string when the speed of sound in the air is 340. Okay, let's do this one too. Right, I think it would be best if I get the rectangle back, or wide rectangle background. Where was it? It was here. Okay. So bear with me. We have 2 frequencies, and of course we have one speed since it is the same medium, correct? All right. So it says if we have 2 frequencies, of course we must have, let's say, as a matter of fact, we have a range of frequencies, you can say. Okay, so find what? Find the range of wavelength. What are the wavelength that lies between these 2 frequencies, you can say, or can be achieved for the range of frequencies of this. Okay, so we have, let's say, we do know that in order to calculate speed equal to frequency times the wavelength, yeah? Okay, since the speed is the same, all right, we have different frequencies, let's say, so we're going to find the wavelength here. So wavelength, let's call it the first wavelength, yeah, equals to speed over the first frequency. That is 340 divided, what is the first frequency? That is 196. All right, so 340 divided by 196. Let's see what the answer is. Okay, and so the answer is going to be what? 1.73, yeah? 1.73 meter. Let's get this back. I think we're not gonna, okay, so 1.73 meter. I think I was correct, yes, 1.73 meter. Okay, that is one. The second one says, by the way, so this is one of the wavelength that we have. For the second wavelength, is going to be same equation, V over, but this time the second frequency, 340 divided by, what is the second frequency? That is 2,673, and of course you get another wavelength. So what is the second wavelength here? By the way, so this range of wavelength is going to be from wavelength 1 to wavelength 2, yeah? The wavelength 1 was 173, and it has to be to the other one. Let's check out the other number, which is basically 0.129. 0.129. It is 0.129. So of course, it says find the possible range of the wavelength in the air that is produced by this. So of course we can say the wavelength that we have, it is going to be in between this range, you can say, yeah? And of course it has to be equal or bigger than this, equal or smaller than this, and then equal or smaller than this one too. Or you could say something like this one here. I think it would be more proper if you put it this way. So we can say wavelength is bigger or equal to this, and of course it is smaller or equal to this volume. Okay, because as the frequency increases, and of course the wavelength decreases. Okay, moving on. We have waves transfer energy. Now remember this, what is the purpose of having waves and all that? Now one thing that waves do, of course, they transfer energy. Do they transfer the particles of the medium? The answer is no. Okay, so now that is a new concept we can say, but still related to waves because we're talking about waves. So waves transfer energy. Waves transfer energy by the vibration of the matter rather than moving, or let's say by moving the matter of the medium itself. So in another way we can say waves only transfer the energy, let's say through the medium, not moving or transferring the particle of the medium. So that is a very important point you need to know. So waves transfer energy by the vibration of the matter rather than by the transfer of matter itself. They don't transfer the matter. Okay, for example, do you remember what happens when you drop a pebble into the water? Let's say of a pond, let's say the water wave that is produced carries a certain amount of energy, but of course the wave transfer energy from one place on the pond to another place to another point, while the water remains in essentially the same place. For this reason, waves are often able to what? To transport energy efficiently. Now here's a question, says, what does the rate of energy transfer of a wave depends on? Yeah? That is of course very important. Let's say we said that waves do transfer energy, yeah? But what does the rate of energy transfer depends on? The first thing we can say it depends on the amplitude, or we can say it depends on the amplitude in general. In another way, the greater the amplitude, the more the energy that is transferred, or that is that the wave is carrying, for example. Let's say, what happens when you drop a small pebble into water? Of course, it will produce ripples that of low amplitude. But what happens if you, let's say, drop not a pebble, this time a larger rock into that pond of water? Of course, you will see that it creates larger ripples, yeah, larger water waves. These larger water waves, that means these water waves are carrying more energy than the waves that were created by a pebble. Okay, so we can say the greater the amplitude, the more the energy that is carried in a given time interval. Now, something that is very important, of course, how does the energy transfer a mechanical wave change with the amplitude? We know that energy transfer or transferred is directly proportional with the square of the amplitude. Now, that is a very good point, and of course, we need to make a pause on this. So, the energy, all right, that is transferred, let's say by a wave, is directly proportional with the square of the amplitude, which means that, for example, if we increase or if we double the amplitude, by what factor will the energy transfer increase? We can say, so in this case, if the amplitude is doubled now, or let's say doubled, of course, then 2 squared in this case, it becomes what? It becomes 4. So we can say the energy transferred will change, right, by a factor of, or the energy transfer will increase by a factor of 4. Yeah? What if we say, by what factor will the energy transfer change if we triple the amplitude? If we triple the amplitude, of course, 3 squared in this case, that means 9. Yeah? So of course we can say that the energy will increase by a factor of 9. But what if we do the reverse of this? What do I mean by the reverse? Not the reverse. What if the amplitude decreases first? Yeah? Let's say the amplitude of a certain wave, let's say, becomes half. Yeah. So let's say this time the amplitude, all right, we know that the energy is directly proportional with the square of the amplitude. So if the amplitude is half, so what is 1 over half squared? 1 over half squared, it becomes what? It becomes 1 over 4. That means the energy, or the rate of energy transfer, will decrease by a factor of 1 over 4. Or you can just say the energy transfer will be 1/4 of the previous one. Okay, now that is 1, yeah? Now let's switch it up. This time, like, what will you do if they give you, for example, the energy transfer and they want you to find, let's say, the amplitude, yeah? We do know that, we just said it, that energy is directly proportional with what? With the amplitude squared, yeah? Now, imagine we have the energy transfer that is, let's say, 16, yeah? Okay, could be 16 joules or whatever, yeah? But let's just say this is a rate without any unit at all. So what is going to be, for example, the amplitude in this case? We said the amplitude is going to be, or by what factor will the amplitude, what will be the factor for the amplitude here? We said amplitude is directly proportional with the, or energy directly proportional with the amplitude square. So remember this, if we're trying to find the amplitude is square, but we don't want square, yeah? So in this case, you will have to take the square root for both sides. These two will cancel out. So amplitude, you can say the square root of 16 in this case is going to be 4 in here. So once again, now how do we summarize this? If you're given the amplitude and you want to find the energy, of course you will square the amplitude, then you will find the factor. But if you're given the energy and they want you to find the amplitude, then of course you will take the square root of the energy to find the amplitude here. So see whichever is given, and then you can of course use the correct relationship to find whether if it is the amplitude or the rate of the energy transfer. Okay. By the way, these are just directly proportional. That doesn't mean equal to. Okay. So if the amplitude doubles, the energy transfer will be 4 times bigger. If the amplitude is halved, what will happen? Then of course the energy would decrease by a factor of 1/4. And this is basically what I have just told you. But do you remember, like previously in the mass spring system, or in a simple pendulum, the amplitude of the wave gradually diminished over time as the energy was what? As the, let's say, energy was dissipated. Do you remember we said, if we have, let's say, talking about an ideal system, if it is a mass spring system, you let it oscillate once, it will oscillate infinitely forever. Whether if it is a mass spring system vertically, let's say horizontally, or if it was a pendulum, doesn't matter, yeah? If we assume that the system is ideal, which means there is no friction, there is no air resistance, then the pendulum or the mass spring system will swing forever. But we know that in real system or in the physical world, this doesn't happen. So you would see that soon after the pendulum or the swinging gets less and less and less until it slows down until it completely stops, let's say, or comes to a rest. Why does this happen? Of course, that is because of the air resistance and friction, yeah? But this slowing down in terms of swinging, of course, it is called damping here. Why? Because the energy would be dissipated because of friction and resistance, so there would be less and less and less energy, and of course until the entire oscillation or the entire system stops. Okay, so this slowing down in terms of frequency here, or the oscillation, of course, this is what is called damping. And if I draw something similar to you for this, let's say in this matter, that'll be something that oscillates like this, and then slowly afterwards is going to completely stop. So you can see that there is a change in the, let's say, amplitude, and changing, we said that energy directly proportional to the square of the amplitude, so the amplitude decreases more and more and more until there is no energy for the oscillation. And that is, of course, this, let's say, energy dissipation is basically what is called damping for swinging materials or objects. It says, what is one advantage of transferring energy by electromagnetic waves? Yeah, remember, one thing that electromagnetic waves has, mechanical waves or let's say longitudinal waves do not have, is they can travel so fast. That is one thing. Second of all, electromagnetic waves can travel through space where longitudinals cannot without a medium. Okay, or we can say their ability to transfer a large amount of energy very quickly. That is one. Or you can say because they have the ability to move through empty space or vacuum. All right, moving on. Section review 3.3. It says, as waves pass by a duck floating on a lake, the duck bobs up and down but remains essentially in one place. Why doesn't the wave carry the duck along the direction of its propagation? Okay, now, I'm not very good in drawing a duck, but I'll draw something better. Not better, something different. So if these are the water waves, let's say, let me remove the whole thing. These are the water waves, let's say. Okay, now instead of having a duck, of course, let's say we have, Let's use something better, perhaps. Okay, let's use something like a football here that floats over the water. All right. Now, what happens as the waves passes? And of course, you would see that this football here would be moving up and down. So if we assume that this is the rest position here, at this point you can see that it is moving up, and a point here, let's say, if it was there, of course, it would be moving downward here, let's say. So you can see that this football, whether if it is a football, whether if it is a duck or whatever, I mean, if it is floating, of course, the object would be only moving up and down, without changing their location. What does this tell us? This would tell us that the waves are only transferring energy. This would also tell us that the waves are not carrying the particles of the medium, because if we consider this to be a particle, you would see that this one does not change location. If it doesn't change location, that means the particles of the medium are not carried with the waves, yeah? Only the energy. Okay, so because the disturbance move not the medium, the energy, you can say, move not the medium, yeah? Or it's just the motion. The motion of the wave will carry the energy, not the particles. Now, it says, sketch one of the following waves that appear on a string, yeah? A pulse wave that is longitudinal, all right? So remember, if we're talking about a pulse wave here, of course, you can either draw, let's say, we're just drawing one pulse. So if it is a longitudinal, we could just draw, for example, one pulse here, yeah? That is, let's say, one compression, or it could be one rarefaction, let's say, yeah? That is basically one pulse, okay? Second, it says a periodic wave that is longitudinal. If it is a periodic wave, of course, then we would have, let's say, compression, rarefaction, because it is periodic, so it is going to repeat another compression, another rarefaction. So you can see that this will always repeat, yeah? And of course, these are repeating, so this is basically what is periodic. Okay, then the next one that we have says a pulse that is transverse. You do know that transverse, yeah? So if we're going to draw a pulse, of course, we can just draw, for example, one pulse that is upward, let's say, and of course, or it could be one pulse that is downward, and then this pulse would be moving, let's say, to the right in this case. If it is a periodic wave, and of course, it has to be something that continuously or repeatedly happens, yeah? This is a periodic transverse wave, yeah? Very good. Now, what about third one here? It says, draw a graph for each of these waves described in terms of, in items of B and D of question 2, and label the y-axis of each graph with the appropriate label, let's say. Label the following on each of the graph: crest, trough, wavelength, and amplitude. Okay, so says the waves described in B and D. In D, this is a periodic transverse wave. In B, there is a longitudinal periodic wave, yeah? Okay, but something that is very important, remember this, we can only convert longitudinal to transverse wave if we, for example, convert, let's say, these longitudinal waves into something like electrical signal, then we can see this on an oscilloscope. Okay, so of course at the highest point, that was the highest pressure, and we've mentioned earlier that this point here represents the compression, where the pressure is the highest. Where the pressure is the lowest is called rarefaction, yeah? And you do know that the highest point can also be called crest, the lowest point can be called trough, okay? And of course the distance between one compression to the next compression, the distance between, maybe I can do it on the wave as well. So let me rewrite this one, perhaps, right on the wave. So we could do something like this. If I, let's say, okay, if this is the wave, we could, no, actually. Let me go back. Let me, so do the wave like this. Okay, now I think it's better. So this point represents the compression. Okay, and this is, by the way, is compression. There's rarefaction, compression, rarefaction, and so on. And so we can draw this, if it is as a transverse wave, this point here would be the highest point. So this is crest, and this is the trough, yeah? Would represent the rarefaction. This is compression. And then, of course, it goes on and on. But remember, the distance between one compression right? Or we can consider this to be the top of the crust or the crust, then to the next crust, to the next compression, that is one wavelength, yeah? Or the distance between, now I can remove this, the distance between one rarefaction to the other rarefaction, that is also one wavelength. So the distance between this to this, that is one wavelength. This to this, that is one wavelength. This to this, one wavelength. Or we can start from this. Rarefaction to rarefaction, that is one wavelength, yeah? Rarefaction to rarefaction, that is also one wavelength. I don't think you have any problem with the other wave. This is easy, yeah? Crust, trough, that is wavelength. And I think that's all what they want, yeah? It says crust, trough, wavelength, and the amplitude. I forgot the amplitude, by the way. So the amplitude would be, let's use red. The amplitude is going to be the maximum displacement from the rest position or equilibrium position. What about the amplitude, let's say, for a compression, or let's say longitudinal wave? Can we say, okay. Can we say this point to this point right here would be considered as an amplitude? Would that be correct? I would like to have this for you guys. Okay, remember, so we said from crest to crest, yeah? So crest, that is going to be what? That is going to be the compression, right? This is going to be what? This is going to be rarefaction, yeah? So remember this, if this is, let's say, 10, so half of it is going to be 5, yeah? So if we assume that from the center to center of this, that is going to be what? That is going to be half a wavelength, but for amplitude normally is going to be half of that, yes? So of course we can say something like this, that would be the amplitude. It's a little bit challenging actually to calculate or to find the amplitude right here. So that this is one of the reasons why we convert that longitudinal wave into a transverse wave, and then it would be best to calculate or to determine the amplitude right here. I hope that was clear enough. Okay, and then now we have section 3.4, which is wave interaction. Now that is a very interesting one. Normally, what we have in here is, you see these bumper boats in water, yeah? Now, what happens when these bumper boats are approaching and colliding with one another? Of course, they will change the direction. Why? Because now each bumper boat has a, let's say, taken a specific volume or space, let's say, that cannot be taken by another bumper boat, let's say. But we know that in physical world, this is how things are. For example, if I'm taking one space, no other objects will take this space. For example, let's say the TV or your laptop, or let's say the desk that you're, let's say, sitting on. And this desk is taking a space, so no other object is taking that space because of that, yeah? That's one thing. But is it the same with, for example, electromagnetic waves? The answer is no, because electromagnetic waves are different, yeah? These are not something like physical, so of course they can move through one another without taking, let's say, the space, let's say. Okay, or another way that we can say two electromagnetic waves can pass one another. Let me give you another example. Let's say two cars are approaching one another heads on, let's say, and then they collide, yeah? And because they are physical, they're made of matter, so these two cars cannot pass through one another, okay? But then if these cars were waves, of course, they can pass through one another, and then after they pass through one another, each one of them could move in their own direction without anything happening to these, let's say, cars at all, yeah? But of course, this doesn't happen in physical world, you can say. Okay, so the two bumper boats cannot occupy the same space, but of course, if they were waves, they could do that. So different materials of objects, let's say material objects, can never occupy the same space at the same time. But when we have two waves, of course, they do not bounce back as bumpers do, for example. Why? Because mechanical waves are not matter, but rather that would be, let's say, transverse waves, or it could be mechanical too, because these are, let's say, not matter, but rather displacement of matter, you can say. Okay, it would be best to see this within the electromagnetic wave. So remember this: two waves can occupy the same space at the same time. That is the difference between waves and, let's say, matter. So now we have, let's say, a principle. Before the principle, we have a term here, and that is called superposition. What is superposition? Okay. Now, take a look. We have superposition principle. I don't know if you've heard of, if not, okay, we're going to go through this. But what is what is the superposition? We can say superposition is basically the combination of two overlapping waves. When two waves overlap, of course, we're going to add them or subtract them. We're going to get into the details in a second, yeah? But when we have two waves, okay, this combination of these two waves, of course, is what is called superposition. Now, if that is the superposition, so what is the principle of superposition? We can say the principle of superposition is basically when two or more waves meet in the same medium, their displacement of the particle is basically, of the medium, is the resultant of the displacement of the individual waves. Now, let me summarize this for you. We said superposition is the overlapping of two waves, yeah? The combination of two waves. And what is superposition principle? We can say superposition principle is this. When two waves overlap, of course, now we'll add the displacement of the resultant wave would be the combination of the two, or the resultant. I think I made it way harder than what it looks like. Okay, so let's try again. Okay, the superposition principle tells you that, for example, when two waves meet, their displacement would be added, yeah? Or the resultant displacement is the combination of the individual waves. Okay, now let me draw something to help you understand what it is. Let's say we have two waves, yeah? Let's say there is one wave that is going this direction, and of course there is another wave that is going to this direction. When these two waves are combining, for example, they meet at a point here. Let's change the color. Okay, and let's choose blue. So of course, once they meet at this point here, if this is 1 and 1, so of course we're going to add their, let's say the displacement of each wave in here. So of course we'll get a total of, let's say, 2 here. If this is 1, this is 2. So this is exactly what do we mean by this. So the displacement of the resultant wave will be the combination of the individual waves. So if this is 1, okay, and then we add the other one 2 here, so we get a total of 2. That is in terms of, let's say, the amplitude or the displacement, you can call it. Okay, so let's summarize this real quick. Superposition is the combination of two or more overlapping waves. That's one. Superposition principle is when two or more waves overlap, you can say, or meet in the same medium. Of course, you can say the displacement of the particle would be the resultant of the displacement of the individual particles or waves. Superposition principle can apply to all types of waves, okay? Whether if it is mechanical or electromagnetic waves. Each wave maintained, that is one thing very important. After the two waves separate or move apart, then of course each one of the waves will regain their original shape and displacement, you can say. Okay. Now, displacement in the same direction produce constructive interference. Okay, now we have something called constructive interference, yeah? Let me draw this, and of course we will go through the definition afterwards. Once again, let's say we have two waves, yeah? And of course, this wave is moving to the right, and then there is this wave that is moving to the left. What happens when these two waves are meet in the same medium? And of course, based on this, because if this is the equilibrium position, this is positive, and this is positive, or you can say this is above the equilibrium position and above the equilibrium position. So what happens when these two waves overlap or meet at this, or let's say in the medium? So of course, like we've mentioned earlier here, the resultant of this wave, of course, is going to be the combination of this and this, yeah? So we will get another wave that has an amplitude, which is, let's call this one wave 1 and call this one wave 2. The amplitude, or the resultant amplitude, is going to be, let's say, the amplitude of wave 1 plus the amplitude of wave 2. So you can see here the resultant amplitude is the addition of the amplitude of each of the waves. What happens after the waves pass or spread? They will each gain their original shape with each, let's say, if we assume that each one of these has 1, let's say, meter of displacement, then of course each one of them will get 1 meter, 1 meter. Okay, but then the resultant of this is going to be 2 meter. That is basically, when this happens, we call it constructive interference, yeah? So what is constructive interference? It is a superposition of two or more waves. We just draw two. There could be more, by the way. Or two waves in which the individual displacement on the same side of the equilibrium position are what? Are added together, and of course to form a resultant wave where the amplitude of the resultant wave will be bigger than the individual particles. Now take a look at this one here. We have two waves, or two pulses, you can say. This is one, this is two. What happens after, for example, they approach? This is the point where they're about to meet, and then after that we have point C, where you can see the resultant. Let us get a pen. The resultant of this amplitude is the combination of the two amplitudes there, yeah? So now this is one amplitude, this is the other amplitude. Once you add the two, of course, you get this amplitude right here. And that is basically what is the constructive interference. And that is not all of it, yeah? What happens after the two waves pass one another? Then you can see that this wave, now after that it goes back to its original shape, and then the other one goes back to original shape, and they are moving away from one another. But once they meet at this point here, that is what is called constructive interference, because their individual displacements are added together. When do we do if the waves were not on the same side? Of course, that is a different story. We will get destructive interference. And there are two types of destructive interference. There is weakening destructive interference, and there is a complete destructive, but save that for later. For now, how we can summarize constructive interference? We can say constructive interference happen if the displacement are on the same side. If the displacement are on the same side of the equilibrium, as in the figure, then of course their amplitude will be added, yeah? And of course we get a bigger amplitude than each of the individuals, let's say. Okay, and then if they have the same sign, you can see that this is, if we assume that this is the equilibrium, this is positive, assuming that upward is positive and below the equilibrium is negative, so the same sign, so we will add them. Okay, now the resultant displacement is larger than the individual displacement. By the way, we could have done this if the waves were, let's say, below the equilibrium as well. Let's say this is one of the wave, this is the other wave, and of course now this time here, these are negative, yeah, assuming that the equilibrium is basically up is positive, below is negative. So in this case, of course, once these two waves meet, of course, we'll get a wave that is, let's say, bigger than these two, of course, because these are in the same direction. If they are in the same direction, we add them, but of course it's going to be negative, let's say. So if this is -1 and this is -2, let's just assume that this is going to be -3. We will add them, but we'll keep the same sign there. Okay. And for the fourth point here, the energy is the total of the energy of the two waves. And of course, each one of these waves are carrying energy, yeah? So the energy, or the total energy, will be the addition of both waves if we have two waves interfering. Or 3, that is going to be the energy of 3, and so forth. Okay. Now what happens if displacements are in opposite direction? All right. Displacements in opposite direction produce destructive interference. So we did talk about constructive interference, yeah? When does it happen? Of course, when two waves meet at the same medium, let's say. And then it happens, let's say, when the two waves are, on the same side of the equilibrium, whether if it is upward, they both has to be upward, or they both has to be downward. And then once they meet, of course, we'll add their amplitude together. Okay, if it is positive, we'll add them, but we'll give it a positive sign. If negative, we add them, but of course we'll give the negative sign back. Okay, but we are going to add their displacement, or we'll add their magnitude of displacement if I disregard the direction. Okay, now what about destructive weakening interference? Remember, we have two types of destructive interference. There's weakening, where the two waves, one of them has a larger amplitude than the other one. So once they interfere, it just makes the resultant wave, or the resultant amplitude, to be weaker, to be less than the amplitude of the, let's say, of the wave with a larger amplitude, okay? And then that's what it is, yeah? Okay, we'll see more of this. So in destructive, of course, the pulses are on opposite sides. So one of them is above the equilibrium, the other one is below the equilibrium, okay? We're going to add them, but don't forget the negative sign, just like this one. Let me draw this one for you as well. Let's say we have two waves. Let's say this is one, okay? And if we draw this one here, let's say this is basically 1 and this is 2, okay? And then let's say we have another wave. This is 0, and let's make this one 1 here as well. Okay, so there is a wave that is moving to the right, there is a wave that is moving to the left. Yeah, what happens when these two waves meet, of course? So the resultant of this is going to be, let's say let me use different color. So let's say this is one of them. Remember, we have 2 in here, and then the other one is going to be, let's say, 1 here, okay? Now, if I draw the resultant in red, we're going to get something like this, okay? So the wave that we will get is going to be something like this. Remember, this is, let's say, 1, this is 2, this is 0, 1 negative here. So this resultant here, if this is 0, this is going to be positive 1 here, okay? Why? Because one of this will be cancelled with, let's say, part of this here, so we will only, we're left with, let's say, a unit or 1 unit of the amplitude here. So based on this, we can say whenever we have a weakening destructive interference, the resultant of the amplitude or the amplitude of the resultant wave would be less than the amplitude of the wave with the greatest amplitude. Remember, this is very important. We cannot say the amplitude will be less than the amplitude of, let's say, of the individual waves, because it could be bigger than this. What if we have, let's say, a different case? The amplitude of one of the waves were 3, the amplitude of the other one was 1, let's say. So the resultant wave we get, of course, it will be, let's say, 2, yeah? So of course 2 is bigger than this, so we cannot say the amplitude of the resultant wave will be smaller than the individual amplitudes, not necessarily. So, but it is always, the resultant amplitude will always be smaller than the amplitude, let's say, of the wave with the greatest amplitude here. Okay, so hope the idea is clear enough. After the two waves separate, of course, they will, let's say, go back to their original shape. And this is the reason, because the resultant amplitude will be less than the will be less than, let's say, the amplitude of the bigger one. That is why we called it weakening. Yeah, it just weakens the let's say the wave with a bigger amplitude. So pulses are opposite side or on opposite side of the, let's say, equilibrium position. The displacement have different signs. So the one that is above is positive, the one that is below is negative. Then the resultant displacement is smaller than the displacement of the bigger wave, we can say. And then amplitude of the resulting wave is going to be A1, that is the bigger wave, minus amplitude of the second wave, weakening interference. That is basically what happens there. The energy is reduced. In the previous one, the energy increases because you're adding both amplitudes. But here, because you're subtracting their energy or their amplitude, so the energy will be reduced. And then after the waves passes or after the pulses separate, their shapes will be unchanged. Okay, now let's talk about the third type of destructive interference. In destructive interference, if it is a complete destructive, this is what you see. We will have two waves, and these two waves are, let's say, completely opposite to one another, and they have the same amplitude, but they are moving in different direction, and one of them is above the equilibrium, the other one is below the equilibrium. So for example, something like this. Okay, so here's a wave. Let's say if I have this one, let's say 2 units above the equilibrium, that is positive, and then of course the other one would have 2 units let's say below the equilibrium, yeah? So once these two are meeting, for example, these two would completely cancel one another out and we get no wave at all. This is what is called complete destructive interference. One of them is positive, the other one is negative, and of course they have the same unit in terms of, if the amplitude is 2 unit above the equilibrium, it is 2 unit below the equilibrium, then we get 0 as a resultant amplitude. Okay, so the pulses are on opposite side. That is one of the conditions for this to happen. The two pulses are equal of amplitude and have different signs, one positive, one negative. Then the resultant wave or the resultant wave has zero displacement, zero amplitude. And then we can say resultant A1 plus, now let's say negative A2, will get zero complete destructive interference. The energy is zero because there is no energy left. I mean, there's no amplitude. We said energy is directly proportional with the square of the amplitude. No amplitude, no energy. That is that simple. After the pulses separate, the shapes are unchanged. After the pulses separate, of course, each one of these, of course, will continue their motion without being changed at all. And that is basically about destructive interference. So remember this, we talked about constructive interference, we talked about weakening, and of course, destructive interference as well. It's very important to make sure you practice all this. Okay, now let me tell you one more thing, and of course we'll end our session with, and that is of course the phase difference. When do we have, remember, if two waves are, okay, if two waves are on the same, let's say, if the two waves are overlapping, you can see here, these are two blue, let's say, and of course they have, their amplitude will be in the same direction, so of course we will add their amplitude, so of course we will always have constructive. Okay, remember this, if one of them goes to the right, the other one goes to the left, that's one. Second, by the way, the phase difference between these two, of course, is going to be zero. But if the two waves are in opposite direction, let's say this is one of them, and then this is the other one. Of course, let's say one of them goes this way, the other one goes the other way direction. So you can see here, if crustes were, let's say, above crust, then the phase difference between the two is going to be 180 degrees, and of course in 180 degrees we will always have total destructive interference. This one will hold more, but I'm going to save it for next session, inshallah. For now, just remember this, when two waves are overlapping, the phase difference is zero, then of course you get constructive interference. If we have something like this, crust over crust, that is destructive interference, and the phase difference here is going to be 180 degrees. Until next lesson, please keep practicing, and I'll see you then. Assalamu alaikum wa rahmatullah.